Hello, my name is Jeff Messier. I'm a professor in electrical and computer engineering in the Schulich School of Engineering, and this is Module 32 in my Computer Networks lecture series where I talk about public key encryption. Now, public key encryption is a topic that I really enjoy teaching for a couple of different reasons. One is that it's a great example of how a bunch of different ideas from a bunch of different thinkers spread literally over, hundreds of years can be all gathered together to solve a really relevant modern problem. So as we're going to see, the inventors of public key encryption used ideas and concepts that were developed literally hundreds of years ago in order to get their scheme to work. The other reason why public key encryption is so important is that, without exaggeration, there would be no online commerce on the internet today without public key encryption. So we've already talked about symmetric encryption, where the same key is used to encrypt and decrypt messages. And the stream cipher that we introduced in the previous module is literally the style of cipher used to encrypt HTTPS encrypted web traffic. However, there's still one very important problem. How do we communicate the key? So if the same key is used to encrypt and decrypt messages, how does Alice let Bob know what key she wants to use? Eve can eavesdrop on anything that is sent between Alice and Bob. So if Alice just simply tries to send the key to Bob, Eve will be able to snatch it. And so public key encryption is important because it allows us to distribute our symmetric encryption keys. And basically the way that public key encryption helps us is that it provides us the use of both what's known as a public key and a private key. And I'll go into this in a little bit more detail as we get into the module. But basically, what Alice will do is Alice will send her public key to Bob over the internet. Eve will be able to fully see and capture Alice's public key. And Bob will encrypt the symmetric key that he wants to use for the stream cipher for Alice and Bob, using Alice's public key, and send that ciphertext over the internet back to Alice. So basically, he uses Alice's public key to encrypt the stream cipher key that the two of them are going to use to communicate. Now, the way public key encryption works, and we're going to see the details of this as we get into this module, is that you encrypt with the public key, but you decrypt with an entirely different private key. And even though Eve has access to all the details of the public key algorithm and Alice's public key, without the private key, she cannot decrypt the ciphertext that Bob sends back to Alice. And so public key encryption is basically a way to privately communicate symmetric encryption keys so that we can use symmetric encryption for encrypting the bulk of our communication. And the reason why we do this sort of two-stage encryption scheme is that symmetric encryption stream ciphers are very, very fast. Public key encryption is a little bit slower, and so we use public key encryption just primarily for communicating stream cipher keys. And as I mentioned, the concept of public key encryption and the algorithm that we're going to talk about is the Rsa algorithm. And Rsa is named after the three dudes shown right here that invented the algorithm: Revest, Shamir, and Edelman. And these three gentlemen are the ones that developed the public key encryption algorithm. However, they used ideas that go back hundreds of years. So as we're going to see, Euler, who lived in the 1700s, came up with a mathematical relationship that is at the core of public key encryption. And even Euclid, who lived 300 BC approximately. Nobody knows exactly, but 300 BC approximately. And even ideas that he proposed as centuries ago are incorporated into the RSA scheme as well. And so now we're going to dive into the details. And I'm actually going to make use of a video that I recorded a number of years ago on Rsa Encryption. And so you're going to see the video change style here pretty quick. We're going to go from this format where you see me talking and me sort of writing on the iPad to more of an old school style where I've just got an overhead camera over top of a pad of paper, but it's still me, I guess. But it's just more of an analog pen and or pencil and paper style for the rest of the lecture. The whole point of encryption and decryption is to scramble information so a potential eavesdropper cannot decipher it, and it's intended to keep our information secure. And so we can represent the encryption and decryption operations as follows. So let's M represent our plain text message. So this is the information that we would like to communicate to somebody else, but keep secret while the information is being transferred to that other person. Or sometimes this could just be information that we have on a storage device like a hard drive that we want to be able to access ourselves, but we don't want an unintended observer to be able to access. C is what we refer to as our ciphertext. And the ciphertext is the scrambled or encrypted version of the plain text. And we represent the encryption operation as a function E. So this E represents the encryption operation that converts the plain text message into our ciphertext. So in order to recover our plain text message from the ciphertext, we perform decryption. And decryption we represent as another function that operates on the ciphertext and returns our plain text message. And so one way to do encryption and decryption is to create a secret algorithm, and we keep the operations of E and D secret so that if somebody accidentally stumbles or overhears our ciphertext, they can't recover the plain text because they don't know the workings of our algorithm. However, a long time ago, somebody named Kirchhoff recognized that it's very difficult to keep an entire algorithm secret. And also, it's very difficult to keep coming up with new encryption algorithms over and over again. So every time you want to communicate with somebody different, or every time someone compromises your encryption algorithm, you have to come up with a new one. And so he recognized back in the 19th century that encryption should work even if the workings of the encryption and decryption algorithm are known. And instead, the secrecy of the encryption and decryption operations should reside in something called a key. And so we represent our key as the letter K. And so our encryption operation then takes two inputs. We take the plain text message, M, but we also pass a key into the encryption algorithm, and that produces our ciphertext. And then in order to recover the plain text from the ciphertext, not only do we have to give the decryption algorithm the ciphertext, we also have to provide it with the key. And the idea is that even though an eavesdropper might fully know the workings of our encryption and decryption operation, if that person does not know the key, then they are not able to recover our plain text message from the ciphertext. And this makes the encryption and decryption algorithms a lot more efficient. So for example, a key is typically some sort of random binary number, so it's very easy to generate a large number of keys, so we can potentially have a new key every time we want to communicate with somebody different. However, there's still a problem with how we communicate these keys. So, for example, if the two parties that want to communicate with this cipher are physical, actual people, and maybe this is some sort of spy versus spy espionage situation, the two people can meet at a coffee shop somewhere, decide on the key, and then go their separate ways and then use the key to communicate. However, the modern reality of encryption is that we want to use it to protect communications over the internet. And the communications have to be between people or entities that are never physically in the same place. So if I want to use encryption to protect the communication between my computer and my bank, for example, I'm never going to be in the same city as the bank servers necessarily. And so I need encryption to work without having this sort of physical exchange of keys. And solving this problem is what public key encryption is all about. So public key encryption solves this problem by introducing two different keys, what we're going to refer to as a public key, and a second one that we're going to refer to as the private key. And for our communication scenario, the public key is going to be used for encryption, and the private key is going to be used for decryption. And the public and private keys are different, they're not equal. And so we represent this as encryption using the public key to create our ciphertext, and then decryption uses the private key to recover the plain text message. And so we can now set up a communication scenario where we use this public key to secure communications being sent over the internet or an unsecure network. And so we've got three actors in this example. So we have Alice and Bob, and Alice and Bob are our legitimate characters that want to exchange some legitimate information. Alice could represent a bank server, Bob could represent a client, something like that. And I'm just going to draw kind of a timeline for each one. And in the middle, between Alice and Bob, we have a character called Eve. And Eve is the eavesdropper. So Eve is going to try and compromise the communication between Alice and Bob. And so how does public key encryption work, or what does the exchange look like? Well, let's say that Bob wants to send Alice a message that he wants to keep secret from Eve. What will happen first is Alice will send Bob her public key. So the public key is sent out in the open over the network, and Eve will be able to receive and store the public key. Bob then takes the public key and encrypts the plain text message to produce the ciphertext, and then sends the ciphertext back across the network to Alice. Alice then uses her private key. It's probably better if I write it like this. Alice then uses her private key to decrypt Bob's message. And so the interesting thing about public key encryption is how much information Eve has available. So Eve knows the full workings of the encryption and decryption algorithm. That's public domain. Eve has complete knowledge of the ciphertext. Eve also knows the key that was used to convert the plain text message into the ciphertext. And yet somehow Eve is still not able, with all this information, Eve is still not able to recover the plaintext message M without knowledge of the private key. And when you sort of think about this just at a high level, and if you're not familiar with it, it seems almost like an impossible problem. And so the purpose of this lecture is to really get into the details of how public key encryption works, look at all the kind of prime number math and all the mathematical sort of relationships and identities that all work together to make this public key encryption exchange possible. I'm going to start off this discussion by giving you a flawed public key encryption scheme, a public key encryption scheme that doesn't work really very well and has a lot of problems with it, but will help us kind of start thinking the way that we need to think to understand RSA encryption for real. So, I guess, I would start by saying, obviously, the public key and the private key have to be different, right? Otherwise, this would be really incredibly difficult to crack, right? Because we send the public key over the air, and Eve can see it. And so I'm just going to just choose kind of what's going to seem like sort of an arbitrary scheme, but as I said, it's going to help us understand real public key encryption fairly shortly here. So we've got the same timeline diagram that we used before. Bob has a plain text message that he would like to send to Alice. And so Alice starts out by generating the public key and the private key. And so let's say the public key is just some number E, and the private key is another number D that's equal to the inverse of E. All right? So Alice then sends the public key to Bob. So she sends E to Bob. The way we create the ciphertext is basically just by taking the plain text and raising it to the exponent of E. We then send the ciphertext back to Alice, and then Alice uses the private key to recover the plain text. How she does that is by raising the ciphertext to the exponent of D. And because the ciphertext is just the plain text raised to the exponent of E, and D is just 1 over E, the E's cancel, and then we get the plain text back. Okay? So let's do an example with numbers. Let's say our public key is equal to 2, and our private key then is equal to 1 over 2. So we're squaring and then taking the square root of the numbers. And our plain text message is an ASCII string, 4 letters, 121, 111, 100. And 97. So those are the ASCII, the numerical ASCII values that we want to send from Bob to Alice. And so when Bob creates the ciphertext, what he's going to do is he's going to encrypt each byte of the cipher or of the plain text separately. So 121 squared is 14641. 111 squared is 12321. 100 squared, oops, obviously just 10,000. And 97 squared is equal to 9409. And so the ciphertext would then be these sequence of numbers. And then this ciphertext is sent by Bob to Alice. Alice recovers the plaintext. And, excuse me, the, so 14641 to the exponent of a half is equal to 121. 12321 to the exponent of a half is equal to 111, and so on, right? So we take the square root of those numbers and we recover our original plaintext ASCII values. So obviously there's a huge number, well, not a huge number, but I mean some serious problems with this scheme. And I'm going to go through the smaller problems first, and then we'll address like the main glaring problem. The first problem is that we're dealing with floating point numbers here, right? So our private key is equal to 1/2. And we really don't want to work with floating point numbers. We want to work only with integers because it's fast, right? Any encryption scheme needs to be fast. Another problem is that the ciphertext is actually bigger than the plaintext, right? Once we square these numbers, they get to be very, very large, and we need more bits to store them, right? So we basically would need more storage or a higher data rate to transmit our encrypted data compared to the plaintext. And we don't want that either. We would really like to sort of keep the size of the ciphertext to something reasonable. Ideally the same size as the plaintext like we had with the stream cipher. What's the last problem? Obviously this scheme is ridiculously easy to crack, right? So if you have E, you know that D is just equal to 1 over E, and then Eve can recover the plaintext as well. Remember, Eve has complete and full knowledge of the encryption algorithm. So she knows that Alice is choosing E as the public key and that the private key is 1 over E. So this scheme is obviously ridiculously easy to crack. So what we're going to do is I'm going to get into some prime number theory, just some integer number stuff. And what we're going to do is I'm going to come around the easy to crack problem kind of in sort of a circular route. What I want to do first is I want to address the problem of getting rid of having to work with floating point numbers. I also want to address the problem of having the ciphertext get really huge compared to the plaintext. And as we work through those two problems, we're going to basically arrive also at an algorithm where the private key is super hard to guess, even if you have knowledge of the public key. Okay, so the background kind of number theory that we're going to be working through here comes from a lot of different places. Some of it can be traced back to Euclid, who lived 300 years before Christ, and is credited with a number of really fundamental mathematical concepts, including geometry. Some people say that Euclid actually was kind of an editor for a journal or a math society, so a lot of what is credited to him may have just been sort of coming out of their math club, basically. We're going to use some concepts from Euler, who was a Swiss mathematician who lived in the 1700s. And of course, the final sort of putting it all together comes from the discoverer, the three researchers that discovered public key encryption, Revest, Shamir, and Edelman. So that's really who we can give credit for all this stuff too. And so the very first idea that we have to discuss is the first operation we have to discuss is the modulo operator. And so if I write a modulo n, or a mod n, that gives the remainder of the division of a by n. And so some examples, 5 modulo 2 is equal to 1. 20 modulo 10 is equal to 0, because 10 evenly divides 20, so there's no remainder. The modulo operator can also be used to restrict the result of a mathematical operation to be smaller than a certain maximum number. So for example, so the modulo operator restricts the result of a mathematical operation to be smaller than n, right? So if we take some number modulo 2, that the result is always going to be smaller than 2. If we take another number modulo 10, that number is always going to be smaller than 10. And so one of the problems we had with our first public key encryption was it made our numbers too big, right? So if we use the modulo operator, we can sort of constrain the results of our encryption algorithm to fit within a certain number of bits. So for example, if we wanted to take the number 115, and let's say we wanted to cube it, right? Because we're still kind of in this mode of taking something to the exponent in order to produce our ciphertext. So if we wanted to produce our ciphertext, 115 cubed is a fairly large number. But if we took the result modulo 256, we would be guaranteed to still be able to fit within 8 bits, right? And so the result of this operation, if you calculate it out, is 235. So that's a solution to one of our problems, right? So we started with 8-bit ASCII. We took our 8-bit ASCII to an exponent, and the numbers got really big. However, if we take the numbers to an exponent and then we take the modulo, 256, we can still fit within our original 8 bits, and the ciphertext will be the same size as the plain text. So to summarize where we are now, we basically we want to find two numbers E and D that satisfy the following relations. So we want to be able to take our plain text to the exponent of E modulo n, so we're adding this mod operator to make sure we don't our numbers don't get too big, and this produces our ciphertext. Then we want to be able to take the ciphertext to the exponent of D, still modulo n, to produce our plain text. Okay, and again, we're just using the mod operator to keep everything, to keep the numbers from getting too big. And so we know that this works if if D is equal to 1 over E. However, we wanted to get away from using floating point numbers, and we can do this by using something called the Modulo Inverse. And finding the modulo inverse requires us to get into prime number theory just a little bit. So just as a review, what's a prime number? A prime number is an integer that is only evenly divisible by itself, or 1. Okay, so examples of prime numbers are 2, 3, 5, 7, 11. So for example, you can only evenly divide 11 by either itself or 1. There's also something or a concept that's known as there's also a concept called coprime numbers. And coprime numbers, two integers are coprime if the largest number that will divide both of them evenly is 1. And so, as an example of two coprime numbers, 4 and 9. So 4 is not a prime number because it's divided by it can be divided evenly by 2. 9 is also not a prime number because it can be evenly divided by 3. But together, these two numbers are coprime because there's no number that will evenly divide both of these, both 4 and 9. And so another way of saying this is that the greatest common divisor of 4 and 9 is equal to 1. We're also going to be looking at sets of numbers. And just as, again, as a little bit more terminology, the cardinality of a set is the number of numbers in the set, or the number of elements in the set. And we denote cardinality by kind of the magnitude operator. So if we have a set that has the numbers 1, 2, and 3 in it, the number of elements in this set is equal to 3. And so when I do sort of the absolute value operator around a set, that indicates the cardinality of the set. And so the cardinality of that set is equal to 3. If we had a set 10 and 20 that only contains 2 elements, its cardinality would equal 2. So the next thing I'm going to introduce is something that's known as Euler's totient function. And it's not going to be immediately obvious why Euler's totient function is going to be valuable to us, but just stick with me and you'll see how all this works by the end of it. One of the cool things about going into public key encryption in a fair amount of detail is that not only do you sort of get to understand exactly how it works, but I think it also gives you an appreciation of just how amazing an idea this was, right? And how the 3 researchers that developed this idea, it gives you an appreciation of how just incredible their knowledge of math happened to be. So Euler's totient function and we denote this by phi of n. So the Taschen function gives the number of numbers, or the cardinality of the set, that contains all of the coprimes, all of the numbers that are coprime with n. Okay, so let's do an example. So the Taschen function for 10 is the number, gives us the number of numbers that are coprime with 10. And so what are the numbers that are coprime with 10? Well, 1 is coprime because only 1 will evenly divide 10 and 1. 3 is coprime with 10. The only number that evenly divides 10 and 3 is 1. 7 is coprime with 10. And 9 is coprime with 10. 9 is not a prime number, but there's no number that evenly divides 9 and 10. And so the Taschen function just tells us how many of these coprime numbers there are, right? So in this case, there are 4. And so the Taschen function is equal to 4. So in general, the Taschen function is really hard to determine. And this is super important. And it really is where the security of public key encryption comes from in the first place, as we're going to see a little bit later on. So in general, it's really hard to determine the Taschen function unless we have sort of a special case where we know the two prime numbers that, when multiplied together, will give us the argument to the Taschen function. Okay, so just to step back for a second. Okay, so let's let the number n be equal to the product of p and q, where p and q are prime numbers. If we can express n as the product of two prime numbers, then the Taschen function, it turns out, is equal to p minus 1 multiplied by q minus 1. And so does that work with our example? Well, we know that 10 is equal to 2 times 5. 2 and 5 are prime numbers. And so the Taschen function for 10 is equal to 2 minus 1 times 5 minus 1, which is equal to 4. And so it does work. Okay, so this is all very interesting, but what does this have to do with encryption? Well, the next concept is going to help us deal with our problem of not wanting to use floating point numbers. And the concept is what's known as a modulo inverse. So I'll just define it and then we'll do an example. So the number d is a mod k inverse of e if e times d mod k is equal to 1. So let me write that out. And then we'll do an example and you'll see how it works. So the number d is a modulo k inverse of e if e times d mod k is equal to 1. Okay, so we know that if so if we're just dealing with like regular floating point inverses, we know that e times d is equal to 1, right? If d is the inverse of e. So the only thing we've really done here is add this modulo operator, but this, by adding the modulo operator, it actually allows both e and d to be integers. So let me give you an example. So, for example, 5 is a mod 14 inverse of 3. So let's say E is equal to 3, D is equal to 5, K is equal to 14. So E times D in this example is 3 times 5 modulo 14 is equal to 15 modulo 14, which is just equal to 1. Okay? So the idea then is once we take the modulo operator, if we get 1, then the two numbers we're multiplying together are modulo inverses, excuse me, of each other. And so we, if we're using this for encryption, we want, and E is our encryption key and D is our decryption key. We want D to be unique, right? We don't want there to be a bunch of possible decryption keys. And so D is unique as long as E and K are coprime. And I'm not going to show the proof for that, but if you're curious, you can find the proof online. For now, just assume that it's a property of the system that we're working with. And so, is it easy to find D? It's easy for small numbers. Like we can come up with a bunch of different examples, right? Like you can think of two numbers, multiply them together, and then just take the modulo of one less the product, and that's basically the solution. But for larger numbers, it's not quite so straightforward, except that there is something called an extended Euclidean algorithm that can be used to find D relatively efficiently for even really, really large numbers. Oh, actually, I should say that if we know E and we know K, then the extended Euclidean algorithm can find D. So if E and K are known, then D is found using the extended Euclidean algorithm. And I represent this as a function, right? Because in most cases, we implement the extended Euclidean algorithm just as a computer program, basically, or a computer function. So D is equal to some function, extended Euclidean algorithm. You pass in E and K as your argument, and it returns the modulo K inverse of E. Okay, so we're going to use this concept of modulo inverse for the exponents in our encryption algorithm. And so we don't have to use floating point numbers anymore. And so where, I guess, are we, at a high level in this discussion? Well, I guess to summarize where we are now, we want to create our ciphertext by taking our plain text, taking it to an exponent, and then taking the whole thing modulo n. And we want to take our exponent modulo k, right? Because we want to use this modulo inverse idea in the exponent, and we want to then, well, let me draw this a little bit different so it's not, maybe I'll even draw it like this. Then we want to take the whole thing modulo n, just so our numbers don't get too big. Then we recover our plain text by taking c to the exponent of d, again modulo k, whoops, and then take the whole thing modulo n, right? And this allows e and d to be integer numbers, and taking modulo n just keeps the numbers from getting too big. So this would fix two of the small problems we had with our sort of first version of public key encryption. Now it turns out that we don't have to, that we can combine working, we can combine taking our exponents to a modulo operator and then taking our whole number to a different modulo operator. Those two operations can be combined using something called Euler's theorem. And Euler's theorem is really kind of the linchpin of Rsa encryption. And not only does it allow us to work with modulos both in our exponent and with our overall number to keep it small, it actually is where the secrecy of the public key encryption algorithm comes from. Okay, so let's take a look at Euler's theorem. So bear in mind, Euler developed this long before the internet, obviously, because he lived in the 1700s. And he developed Euler's theorem originally not thinking about encryption at all, but really as a mechanism to compute the value of numbers that were taken to a very large exponent. Okay, and so Euler's theorem says that if you take a number a, an integer a, and take it to the exponent of the totient function, right? Remember, we defined this totient function a little bit earlier. And then you take the whole thing modulo n, you get 1. Okay? So for example, and notice we're taking the modulo of n, and that's the same argument for our totient function. So for example, if we took 7 to the exponent of the totient function, where we gave the totient function the argument of 10, and then we took the whole thing modulo 10, we would get 1. Okay? So how is this useful? Well, I'm going to, well, actually, let me, just to sort of like prove this to you, I guess, let me sort of continue this example a little bit more. So we saw on the previous, when we previously looked at the totient function, we know that the value of the totient function for 10 is equal to 4. Remember, the totient function just tells you how many numbers less than 10 are coprime with 10, right? And so the answer was, if I just look back so I can double check what those numbers were, 1, 3, 7, and 9. So there's 4 numbers there, and so the solution of the totient function is equal to 4. And so this term is just 7 raised to the exponent of 4 modulo 10. 7 raised to the exponent of 4 is 2,401. If we take that modulo 10, the result is equal to 1. And you guys can play around with this a little bit if you want. You use smaller numbers, right? Because you can figure out what the value of the Tauschen function is. But as long, as long as you can stick to numbers that are small enough that'll work in your calculator, then you can sort of verify that this is true. The one condition required by the Euler's theorem for all this to work is that the numbers a and n have to be coprime. Okay, so that's Euler's theorem and just how it works kind of by itself. But probably right now you're not seeing really why this is useful. So I want to show you how Euler would have used it back in the 1700s for calculating the value of numbers taken to a very large exponent. And then I'm going to bring it into the encryption. And at that point I'll be able to present Rsa encryption to you, basically how it works, or in its sort of full form, basically. Okay, so to see how Euler would have used this theorem, we need to go back and just review very quickly some terminology related to long division. So let's say let's assume we divide some number L, some integer L, by some other integer that's given by the Tauschen function. Then L is equal to the divisor times the quotient of our long division plus the remainder. And I'll just represent the remainder R. So as an example, so if L was equal to 15, right? And the Tauschen function happened to be equal to 4, then we would say 15 is equal to 4 times 3, which would be our quotient. And so 4 times 3 obviously is 12, plus 3, which is our remainder. So the Tauschen function divisor, this would be our quotient, and then that is that's our remainder. And remember that the remainder is equal to our number 15 modulo the divisor modulo 4. And that's equal to 3. And if you're not sure about that, if you're not sure about what I've just written down here as far as, long division, quotients, remainders, how the modulo operator gives you the remainders, stop the video now and just do some long division practice, okay? Just take some integers, do some long division, find the quotients, find the remainders, make sure you're satisfied that the remainders are given by the modulo operators, and make sure that this equation makes sense, and just forget for now that the divisor is the Tauschen function. Just choose any number for this. Just kind of work with this and get comfortable with that long division again, because if this didn't make sense, then what I'm going to tell you next definitely is not going to make sense. Okay, so now let's put ourselves back in the 1700s And so replace my pen and graph, or my pencil and graph paper with a quill and parchment, I suppose. And let's say we want to solve the following problem. So we want to calculate the number a raised to the power of L modulo n. Why they wanted to calculate this in the 1700s, I really don't know. But this is the problem that they would have been working on. Now, a is an integer, L is an integer, n is an integer. We're assuming that a and n are coprimes, so Euler's theorem can be used. And I want to focus on this exponent L. So this exponent L is generally a really, really big number, right? But let's say we divide L by the tangent function of n, right? Where n is the number we're taking the modulo here. So let's figure out what the tangent function of n is. And let's divide L by the tangent function. Well, we know that if we divide L by the tangent function, we can express L like this. L is equal to Q terms, or Q times the tangent function. So we have basically Q tangent functions all added together, and then we have to add on our remainder, right? So this is equal to A to the L, or sorry, A to the tangent function plus the tangent function plus tangent function plus the remainder modulo n, right? So we've got all these tangent functions. How many of these do we have? The number of terms equals the quotient of our division, right? What is this remainder? This remainder is just L modulo the tangent function, right? And so another way to write this, because when you multiply things together, raised to the exponent, you can add the exponents. So we can just write this as A raised to the tangent function of n times A raised to the tangent function of n times ... A raised to the tangent function of n. And then our final term, which is the remainder, is A raised to L modulo the tangent function. And then the whole thing is mod n. But if we look at all of these terms, we know from Euler's theorem that A raised to the tangent function mod n is equal to 1. So basically all of these terms go to 1, and we're left with A L to the modulo of the tangent function, all taken modulo n. So what have we done here? We basically made the exponent a lot smaller and a lot easier to handle. And so let's do an example, sort of a Euler style example, to show how this works. So let's say we want to take 7 raised to the exponent of 222 modulo 10. Now your calculator can't even do this. You can say, well, yeah, it can. Well, really, it kind of can't, because in order to calculate this, your calculator would express this as a floating point number, and you would lose precision. What we're going to be able to do is calculate the actual integer value using Euler's theorem. Okay, so we can see that 7 and 10 are coprime, right? That's the rule. Otherwise, we can't use Euler's theorem. And we know that the tangent function, of 10 is equal to 4. And so this is equal to 7 raised to the exponent of 222 modulo 4, modulo 10. 222 mod 4 is just equal to 2. Mod 10, which is just equal to 49. Mod 10, which is equal to 9. Okay, and you couldn't calculate this on your calculator. If you wouldn't end up getting 9. So really, the only way to calculate this is using Euler's theorem, which is, you're like, really? Why is this useful for encryption, right? So this is all very interesting, and hopefully you followed this all. So I'm going to now bring this back into the world of encryption. And what I'm going to actually do next is I'm going to show you RSA public key encryption as it exists in real life. And I'm going to show you sort of all of the steps. And then we're going to tie it into how it's related to what we just talked about here. But the one thing, if you take nothing away from this discussion that I've got on this page, the one really important thing that I want you to take away from is the following observation. So if we take a to the L modulo n, it's the same thing So if we take a raised to some integer number modulo n, it's the same thing as taking the exponent modulo the tangent function. So in other words, a to the L mod n is equal to a to the L modulo the tangent function mod n. Said another way, if you take a to the L mod n, it basically takes the exponent modulo the tangent function for free. So if you take a to the L modulo n, then you kind of automatically are already taking the exponent to the modulo of the tangent function. And this is how it's going to tie back to encryption. You remember on the previous slide we said, okay, cool, we want to take our plain text to the exponent of e modulo some number k, because we want to use modulo inverses in the exponent, and then we want to take the whole thing modulo n to keep our numbers small. It turns out we don't have to have a special modulo operator in the exponent. As long as a and n are coprime, then we get them, when we take the modulo n operator for the whole answer, we get the modulo in the exponent for free, basically. And so that's kind of where we're going with this. Let me do a couple of examples, and I'll show you the real RSA encryption algorithm, and then you can sort of see how this all hangs together. Okay, so now I'm going to present to you RSA encryption as it works in full, and we're going to use it to tie in all the concepts that we've talked about up until now. So I think the best approach is for me to just give you the algorithm. You'll start to make the connections yourself, but then we'll go through the discussion, or we'll then discuss the algorithm kind of step by step, and we'll see how each of the concepts we've talked about up until now sort of all tie together. Okay, so let's start with our timelines. We've got Alice, Eve, and Bob. So, maybe move this down a little bit. Rsa encryption, how does it work? Okay, step one. Alice generates two very large prime numbers, and we'll call those numbers P and Q. Okay, so P and Q. Generate P and Q. Then Alice calculates two quantities using those prime numbers. The first one is n. N is equal to P times Q. And she also calculates the totient function for n, which we know is equal to P minus 1 times Q minus 1. Remember, in general, the totient function for very large numbers is super difficult to find unless you happen to know the two prime number factors of your large number. And remember, these numbers are big. So in the current RSA public key encryption standard, n is 2048 bits long, right? So calculating the totient function of a number, 2 to the 2000 bits, equal to 2 to the 2000 is virtually impossible unless you happen to know what the prime number factors of that number n happen to be. Okay, so next, Alice generates her encryption keys. Okay, so next, Alice chooses a random number E that's going to act as her encryption key, and E is co-prime with the totient function. So up here on my timeline, I'm getting a little bit behind here. So Alice has generated P and Q. She's calculated N is equal to P times Q. She's also calculated the totient function. Sorry, my diagram's getting a little crowded there. So if that's our encryption key, we have to also find our decryption key D. And D has got to be the modulo inverse of E. So D is equal to, or D is found using the extended Euclidean algorithm. And so D is going to be the modulo Taschen function inverse of E, right? Before, when we were going through our example, this was just some number k, but I'm specifically choosing our inverse modulo to be equal to the Taschen function, and you're going to see why that's the case in a little bit. So we now have E and D. It turns out that our public key is not a single number. It's actually two numbers, because Bob needs two numbers in order to generate the ciphertext. Not only does he need E, the encryption exponent, he also needs N. He needs to know what to take the modulo, what number to take the mod of for the final ciphertext results. The private key is equal to D. And so up here we've got our public key, E and N. Our private key is equal to D. And now we're ready to go. We send over the public key. Which is E and N. Bob calculates the ciphertext by taking the plain text to the exponent of E, modulo N. He then sends the ciphertext back to Alice, who recovers it by taking the ciphertext to the exponent of D, modulo N. How does this work? Well, we saw on the previous slide that if we take the overall number modulo N, it's the same thing as taking the exponent modulo the Taschen function. And since D is chosen to be the modulo inverse of E, when you take the modulo according to the Taschen function, then D times E in the exponent ends up being equal to 1. And I'm going to step through that in a little bit more detail, but that's sort of big picture what's happening. So just to fill in those final steps, okay, and that is the conclusion of the algorithm. This is exactly how it works. Now, you'll be seeing, probably after looking at this, you're going to see some familiar things. You're going to see how stuff is being tied together a little bit, but I'm sure you still have some questions. And so let's address what some of those questions are. Now that you can see the whole algorithm in front of you, let's step through it and then sort of figure out exactly why this works and why I've sort of tied things together the way that I have. Okay, so the first question you probably have is, how did this work, or how were we able to recover the plain text? So, question 1. this recover the plain text. Well, C is equal to the plain text raised to the exponent modulo n. We know that, so this is how Bob generates the ciphertext. When Alice receives this ciphertext, she takes C to the exponent of D modulo n. However, this is equal to the plain text raised to the exponent of e, right, if we just sort of substitute that in there. And then, of course, everything has to still be taken modulo n. Or in other words, this is equal to m to the e times d modulo n. However, thanks to Euler's Taschen function, we know that when we take things to the exponent of, or thanks to the Euler's Taschen function, we know that when we take this whole result modulo n, it's the same thing as taking our exponents modulo the Taschen function. And since e and d were chosen to be modulo inverses when we take the modulo of the Taschen function, the exponent just reduces to 1 modulo n, and the plain text is recovered. Also, those of you that are following very closely will know that this only works if m and n are coprime, because that's the only time that Euler's theorem works. And it can be proven that they're always coprime as long as the prime numbers p and q used to calculate n are distinct, as long as they're not equal. I won't bother showing the proof here, but you can search it up online if you're interested. Okay, the next question is, how can this be secure? So we know Eve knows E and N. So all Eve has to do is find out D, and she can crack the cipher. So let's look at that. So we chose D. Using the extended Euclidean algorithm, which Eve knows, right? Because Eve has the details of all the source code, so Eve knows how to do this. She knows E, obviously, so she knows the first argument for the extended Euclidean algorithm. And so then all she needs is the second one. She needs to know the Taschen function. However, Eve, it's very difficult for Eve to guess the Taschen function. For us, it was easy. So Alice knows that the Taschen function is p minus 1 times q minus 1. So super easy for Alice to calculate the Taschen function. However, Alice keeps p and q secret. These numbers are kept secret from Eve. So in order for Eve to find the Taschen function, she has to figure out what p and q are. Or basically, a better way of putting this maybe, she has to resort to solving the equation n is equal to p times q. So Eve has to, by herself, figure out the two prime numbers that when multiplied together give the number n, because Eve of course knows n. However, this is super hard for very long numbers. So currently, the world record for factoring, for finding prime number factors for a large number is, I think the biggest number that this has been done for is a 768-bit number or something like that. So, and remember that's 2 to the 768 bits. And currently, the public key encryption standard, n is 2048 bits long. So the fundamental source of public key encryption security is the fact that it's very difficult to find the prime number factors for very, very large numbers. And without knowing p and q, you can't find the Tauschen function, and without knowing the Tauschen function, you can't figure out the decryption key D, and that's where the security comes from. Okay, so just to wrap this all up, let's do an example with real numbers. And these are small numbers, right? So this is not actual public key encryption. If you used public key encryption with numbers this small, it would be ridiculously insecure. Okay, so Alice, first of all, has to generate her two prime numbers, P and Q. And let's say we choose P is equal to 5, and Q is equal to 29. And so that means n is equal to 5 times 29, which is equal to 145. And the Tauschen function of 145 is equal to 5 minus 1, 29 minus 1, or 112. Alice chooses an encryption key E equal to 5. Whoops. Which is coprime with 112. And the extended Euclidean algorithm, when given 5 and 112, would give us a modulo inverse of 45. And because these numbers are so small, we can check that this actually works. So 5 times 45 modulo 112 is equal to 225 modulo 112, right? And 2 times 112 is 224, so we know that this equals 1. Oops. Line this up. So Alice shares her public key, which consists of the number 5 and the number 145, right, E and N, with Bob. And Bob's plain text is equal to an ASCII string, 121, 111, 197. And so the ciphertext is actually going to, we're actually going to break up each we're going to break up the ASCII string and encrypt each character of the ASCII string separately. Okay, so then once Bob receives the public key, he raises each of these ASCII characters to the exponent of 5 and takes the modulo 145. And the result is 51, 36, 35, and 37. And so the ciphertext then is the numbers 51, 36, 35, and 37. So I guess Bob sends this ciphertext to Alice, and Alice recovers the plaintext. As follows, and takes all of the, or takes each of the ciphertext numbers to the exponent of 45, modulo 145, and if you do that calculation, you see that you recover your original ASCII characters. Now, just one thing to note here, you can't do this on your calculator, right? Because what happens when you take 51 to the exponent of 45, it'll go into a floating point number, and then you lose precision, and this doesn't work. You actually have to calculate, well, I guess the easiest way to do it is to write a little computer program where you multiply 51 by its, you multiply 51 by 51 45 times. And each time you multiply two 51s together, you take the result modulo 145. And you just keep doing that for 45 times, and then you get the answer 121.